All right, so welcome to pre-calculus. This is day 5. We're going to focus on graphing exponents or exponential functions. So this is like a basic model that we'll use. All right, y and t. T is going to be our independent variable. That's like x, so that'll be like on our x-axis. And when it's all said and done, that'll be a variable. And y is also the dependent variable. That's on the y-axis. So it's all said and done, y will be y. But a and b are going to be constants that we'll know, and we'll use that to help us graph. But every point t comma y has to be a point on our graph. So we can always plug in values for t to see what y is, and then we can use those points to help pick the shape of our graph. All right, so y is, we'll say it's like the range or our dependent variable, which means like what y is going to depend on what t is. And t is t because for a lot of these word problems, t will represent like time. Like so like y would be the population over time, or like the amount of money in the account over time. All right, a is going to be our coefficient. That's usually going to be, if it's this model, is going to be our starting amount. All right, and that's the coefficient, which will affect like our y-intercept. So I'll also do comma y int for y-intercept. All right, and b is our base. So like that's gonna change based on like how much our model is increasing or decreasing or growing or decaying. So b is gonna be our base. Slash like, I'll put like comma rate of increase or decrease. All right, so first, exponential growth, if it's in this model, it's going to be growth if the base b is greater than 1. So if we're raising t to a power that's greater than 1, then it's going to be growth. It's going to go up. And I'll explain. Well, we'll jump to graph shape real quick. We'll jump to graph shape. That'll be like, all right, increasing. And in the sketch part, I'll draw like a y and an x-axis. Wait, Lucia is in this class, right? Yeah, I just saw her. That's cool. No, I think she's virtual. All right, so I just popped in my head. I'm like, I'm going crazy. Okay.
Yeah, I was like dropping a book. I'm not actually in.
So that's what it looks like when it's increasing. And so situations. Can anyone think of one, like a situation where we have like a growth, exponential growth model? Yeah, investment account, if you're investing to do well, hopefully. I'm like, some of ours in March, but yeah. So, or unless you have Bitcoin in the last couple of weeks. But yeah, so like, a growing investment account, very good. You can see how much is in over time. Anything else? Like a wildlife example? Yeah, population of like, deer or something, like a population. Let's put population. Population growth. All right, and B equals, so that would be like if you ever had to solve for B, we could take that and we could divide both sides by A, and then we have y over A equals B to the t power. And let's say we were trying to get B alone. Can anyone think of the operation that we would do here to get the B by itself? Yeah. Awesome. Yeah. Or you could take like the teeth root, not to be confused with like teeth, like on your mouth, but like teeth, like the first or fourth of teeth. So yeah, teeth root. So yeah, so you raise it to the 1 over t power. And sometimes like that'll be really helpful when when you know y and a and t and not b. So then b would equal y over a in parentheses to the 1 over t power. All right. So that's your base. That's everything you need to know for growth. All right, and decay works the same way. It's just going to be decreasing. So it's like this graph, but like reflected over the y-axis. So if we want to start from the bottom, like Drake, then we would go like this. All right, and now we're here. Now the whole team's here. All right, so the shape is decreasing. And situation, so I think of like a decay situation. Yeah, like a car's value. Very good. Awesome. Yeah, so cars generally depreciating assets, they lose value. And then like if it's like a vintage car, like a car that like they don't make anymore, it could actually increase, but generally speaking, cars are depreciating assets. Value of a car. Excellent. So they used to say never buy a new car. It's like a bad investment, but when you buy a car versus lease it, then like you have to like pay for all the repairs, and those can get expensive. But when you lease a car, they'll cover everything, but you don't own it. So at least if you own the car and like you have an asset that you could sell. So I'm not sure if that's still the rule of thumb, but when you're young, I suggest get like a used car, speed it up a little bit, learn the ropes of the road, and then when you get some money, buy a nice car. So yeah, value of a car. Also like a half-life. I don't know if you guys have done that in like chemistry or last year, but some isotopes will decay and have like a half-life, which means like it'll take that amount of time for it to go from like 10 grams to 5 grams and then 5 grams to 2 grams. An example that you can all relate to is like if you take an Advil or something, that has a half-life of like 2 hours, which is why they say like don't take one every more than 4 hours, because if you take 100 milligrams of Advil, after 2 hours, there's still 50 milligrams in your body, and then 25 milligrams, then eventually it just dissolves. But also caffeine has a half-life. That's why like you may drink caffeine and get woken up, but eventually like it wears off. All right. Oh, actually I did. Okay, so I was listening to Joe Rogan. I want to make sure I got this right. And this is kind of like a dark example. Does anyone know like I forget what it's called? Knox. It's so when someone has a drug overdose. There's like Narcan. That's it. Narcan. So it was a great example, and I wrote it down, but it was like months ago. But basically, like the Narcan like counterbalances the drugs in your system, and there's an issue with them that like the half-life of the Narcan is like less than the half-life of the drugs in your system. So like it works right away, but then like it wears off, and like I forget the exact example, but like because the half-lives are different, like it may wear off, and then you're back to like then you feel the effects again. You know what I mean? Like it doesn't.
Yeah, the half-life of Narcan is less than the half-life of fentanyl.
Yeah.
And if you start immediately overdosing and then immediately get Narcan, then you'll be like awake, but then as soon as the Narcan wears off, the fentanyl is back.
There you go.
Overdosing again.
Yes.
That's why you have to go to the hospital and take Narcan.
Very good. That's exactly what I was thinking of. All right, so you do some drugs, you take them, and they have fentanyl in them. Fentanyl has a longer half-life. Narcan has a short half-life. So you take the Narcan, you're gonna pass out. Take the Narcan, oh, you feel fine. Like it reacts like it does something where it inhibits the drug, like it blocks it.
Narcan gets into the receptors.
Yeah.
It blocks the fentanyl from going in. Since if the Narcan wears off or the fentanyl does, then they'll just lock into the
Yeah, so they're still in your body, so the Narcan wears off fast, you're feeling fine. But then once it wears off, the fentanyl is back. It didn't leave your body, it was just blocking it. And then it's back and you feel the effects again. Which is why, like you said, you have to go to the hospital right away. Interesting. Yeah. I remember writing that down. I listened to it. It would be a great math problem. And then we already did half-life, and I forgot about it. But all right, so we got our basic stuff here. So now let's apply it. Let's turn the page. All right, so when we graph these, we're going to make a table of values because it's just helpful to have some points when we're graphing. And then we'll also see the shape of the graph. So we're going to plug in -2 for x. So that's going to be, y is going to be 2 to the -2nd power, which would be 1 over 2 squared, which is 1/4. So that's going to be our first point. So after we fill in our table, we will start plotting those points. And then we plug in -1. That's 2 to the -1st power. Remember from earlier, a negative exponent means you just find the reciprocal. So that's 1 over 2. And then 2 to the 0 power, anything to the 0 power is 1. Because remember, that means like when you subtract the exponents, it's the same thing in the numerator and denominator, which means 1. And then if you plug in 1, 2 to the first is 2. If you plug in 2 for x, 2 squared is 4. All right, so let's plot these points. Now notice how x could be negative, but y can't be, because even if we keep plugging in negative numbers, like let's say we did another one here, like x and y, and we plugged in like -5 for x, that's still 2 to the -5 power, which is 1 over 2 to the 5th power, which isn't 0, but it's pretty close to 0. So like as x approaches -infinity, y is going to approach 0, but it's never going to reach 0, because the worst that's going to happen is going to be 1 over a really big number, which is still something. It's still something bigger than 0. So we're going to have something called the horizontal asymptote, where the graph's going to like level out and get closer to it. All right, so knowing that, we can make our x-axis kind of lower because we don't have to worry about any points below the x-axis. And then the y-axis will look like that. And then we could plot these points. So like -2, comma 1/4, -1, comma 1/2, 0, comma 1, 1, comma 2, 2, comma 4. And you could see like the general shape of the graph. So starting from the y-intercept, you know, if we did 3, 2 cubed would be 8. So notice how like the distance from the x-axis keeps doubling because our base is 2. So this graph's just going to keep increasing, and that's what a growth would look like. And if b was bigger, it would increase more rapidly. If b was closer to 1, it would be like more level. And then going the other way, it's going to get closer and closer to 0 because it keeps getting half the distance to the x-axis. Like it'll never actually touch it. All right, and let me show you like a quick example on Desmos. So like y equals 2 to the x. All right, so it looks like it's touching the x-axis, but then like if you zoom in, like it never actually touches it. And then here, like, all right, now it's touching the x-axis, but right, zoom in. See, it's not, it's just gonna get infinitely closer to the x-axis and never actually touch it. All right, so now that we got our graph, we can answer all these questions. All right, so domain. What do we think the domain of this is going to be? Do you remember what domain means?
Domain is, how far it is left to right.
Yeah, so like what values of t will this graph hit? What was it? Yeah, very good. It's going to hit them all. So from -infinity to +infinity. So you can write it like that. Excellent. You can also say all real numbers. They both work. So your domain represents all of the inputs that you could plug in and get an output. So that means like all the x values you can plug in and still get a y value. So here, like since it goes left and right forever, you'll get every x value. The range is the same idea, but the y values. So is it going to hit every y value, or do we have to restrict it? All right, so you ever seen like Lord of the Rings? Gandalf, is it Gandalf? You shall not pass, right? And then he dies, and it's crazy. Then he comes back. Oh, sorry, spoiler alert. But See, this horizontal asymptote is like saying this graph cannot pass it. Like it's never going to get below it, and it's never going to reach it either. So the range is going to be y is greater than 0 because it's not going to equal 0. So that's why it's greater than. And it's never going to go below 0. So the only y values that this graph will hit will be positive y values. And then this is the end behavior. So it's describing what happens to y as x reaches either end. So as x approaches infinity, what's happening to y as we move more to the right? It's going up, right? So y is also approaching infinity. Because like this would be infinity on x, infinity on y, negative infinity on x, negative infinity on y. All right, but as we move to the left, it's not really going down, it's sort of leveling out. So what value is y approaching as x approaches negative infinity? 0. Very good. So it never reaches 0, it approaches 0. And this graph is increasing. Now, if you look at it from right to left, it's decreasing, but we don't read from right to left. We read from left to right. So it's going up from left to right, so it's increasing. And the asymptote is this dotted line right here, which is the x-axis, which is a horizontal line that you could describe as y equals 0. And then the intercept is just the y-intercept. It's not going to have an x-intercept because it's never going to cross the x-axis. So the intercept is just 0, 1. All right. Now, if we look at this last example here, can anyone tell me any like similarities or differences between the example we're about to do and the example that we just did? Yeah. Very good. It's going to be decreasing. And if you look, we know, oh my goodness, I totally dropped the ball on this one. I forgot to write base. So for decreasing ones, decay, let's fill that in. That means b is less than 1, but also greater than 0, which is important. You're never going to have a base that's less than 0 because then the graph gets all funky. Because then it's like, well, negative to an even is positive, a negative to an odd is negative, and it literally bounces from like above to below the x-axis. So we don't call that exponential function. So if the base is between 0 and 1, it should be decreasing. So yeah, very good. Now 2 and 1/2 are pretty close to each other, especially with exponents, because 2 is just 1/2 to the negative first power, or 2 to the negative first power is 1/2. So look, if I just change this exponent to a negative x, that's the same thing as y equals 1/2 over x. Because if you apply that negative just to the 2, then it becomes 2 to the negative first power, which is just 1/2. So this graph will look like it'll look like a reflection over the wait a minute. So I'll keep this here. So our graph now is going to look like it's reflected over the y-axis. Because if you remember in geometry, when you take a point and you reflect it over the y-axis, you do that by just taking the x-coordinate and changing it to a negative. All right. So when we fill out this table, we should see the same numbers, just in different spots. All right, so if x is -2, now we'll have 1/2 to the -2 power, which is the same thing as, like, you can apply the negative first and make that 2 squared. All right, and that's just 4. So like exponents, you can apply like one part at a time. Like -2 is just -1 times 2. So if you apply the negative part just to the 1/2, it becomes a 2. And then 2 squared is 4. And then here, if you do 1/2 to the negative first power, it's just going to be 2. And then anything to the 0 power is 1. 1/2 to the first power, that's just 1/2. And then 1/2 squared is equal to 4. All right, so now we'll plot those points. So again, since there are no negative y values, I will lower this x-intercept, or this x-axis, and then plot these points. So like -2, 4, -1, 2, 0, 1, 1, 1/2. Oh my God, I'm an idiot. What?
The 2 use 1/4.
Yeah, definitely. I got excited. There you go. Didn't affect my graph. Saved me just in the nick of time. Although I smelled something fishy when this decreasing function started to increase. Something went off my head. Something's not right. All right. So there we go. So now we could just connect the dots, and it's going to look like a similar shape to the other one. Just going in the other direction. All right, so the domain is still going to be all real numbers. So from -infinity to +infinity, because it still goes left and right forever. The range, y is greater than 0. Now, as x approaches infinity, what's happening to y? Very good. The tribe has spoken.
Sorry.
No, it's a good reference.
What did you say?
I said the tribe has spoken. The tribe has spoken. The tribe has spoken.
I'm just yawning.
All right, x to the negative
Yeah.
infinity. Now it's going up. So y is approaching just positive infinity. So up is positive infinity, down is negative infinity. All right, now we're decreasing because going down from left to right, and also because the base is less than 1. The asymptote is still at y equals 0. And the intercept is a y-intercept. It's still right here at 0, 1. All right, and that's how you graph. So we're going to make a table, plot our asymptote, and then connect the dots. So if you look at the bottom of the page here, it gives you like just some basic rules to help you graph these. So create a table, plot at least 3 points, including the y-intercept, draw a smooth curve, say the domain and range, and the horizontal asymptote. So this is the model that you're following every time. All right, so you got about 25 minutes left. So I want you to try some of these, all right, which involves graphing calculators. If you don't have a handheld graphing calculator, that's fine. You can use Desmos, and you can use this. I got another one too, but everyone else, if you have a Chromebook, you can use Desmos, or if you want to use the handheld, you can use mine. All right, I'll walk around and help you out, but if I'm not walking around, you can ask me for help. And I'm going to pause the video now.